Diyos. Maraming salamat po sa buhay at lakas na aming taglay, sa liwanag ng kaisipan at sa pagkakataong maipagpatuloy ang pag-aaral ng mga kabataan. Gabayan mo po ang bawat isa sa amin. Anuman ang bahagi na aming gagampanan, naway maging maayos at matagumpay ang pagtuturo at pag-aaral na aming gagawin sa araw na ito. Patawarin mo po kami sa aming mga pagkulang at pagkakasala. At sa aming paggawa, ikaw po ang aming makasama. Amen.
Good day, everyone. Welcome to our Earth Science virtual classroom. I am Ma'am Chealand Dela Cruz of Malinta National High School. Join me in this another amazing and fun-filled discussion as we continue to unravel the beauty and wonders of planet Earth. The topic that we are going to discuss today is all about explaining how the movement of plates leads to the formation of folds, faults, trenches, volcanoes, rift valleys, and mountain ranges. This was taken from the list of most essential learning competencies given by the Department of Education. Specifically, at the end of today's session, you should be able to explain the relationship between theories of continental drift and plate tectonics, differentiate the three types of plate movement, and identify the topographic features associated with plate tectonics. But before we delve into this topic, let us have first a short recap of what was discussed last live stream session. Can you still remember it? Very good. Ma'am Advincula of Bignay National High School discussed about weathering. According to her, this exogenic process is the physical breakdown or chemical alteration of rocks at or near the Earth's surface. It has two types. It can be mechanical weathering, wherein rocks simply disintegrate or break into smaller pieces without changing their mineral composition, or chemical weathering, which decomposes rocks through chemical reaction, leading to changes in their mineral content. Do you have any question about this topic? If not, I guess we can now proceed to our lesson. So prepare your pen, paper, and self-learning modules. To begin with, let's have a simple activity called Locate and Drag Me game. To play this game, I want you to copy and open the given link. You may use another gadget or you may open it using your respective browsers and return to our virtual classroom once you've accomplished the task. In this activity, all you have to do is to locate the current position of the 7 continents of the world by dragging and dropping their name in their respective areas in the map. You have 1 minute to finish this game. Time's up. Did you get the correct answers? Very good. Let's see. The green and biggest continent in the map is Asia. The small blue continent below Asia is Australia. The violet continent beside Asia is Europe. Africa is the pink continent below Europe. North America is the orange continent located on the western part of the map. Below it is South America, and the white continent in the southern portion of the globe is Antarctica. Altogether, these land masses make up the 7 continents of the world. But did you know that the current positions of our continents was viewed to be totally different from how it looks like 250 million years ago? 3 personalities to believe that the continents had once formed a single landmass before breaking apart and drifting to their present locations were Francis Bacon, the first scientist to notice that there's an odd puzzle fit between Africa and South America in 1600s. The second scientist was Antonio Snyder Pellegrini, wherein he enhanced Bacon's discovery by comparing the coastlines of Africa and South America in 1858. Between then and 1912, other people identified further similarities between other continental coastlines. But it was only in 1912 that Alfred Wegener published a theory to explain why the Earth looked like a huge jigsaw puzzle. He called this continental drift hypothesis. He suggested that a very long time ago, all the land that covered the Earth had been joined together into one huge continent. He named this landmass Pangaea and proposed that millions of years ago, this supercontinent had somehow broken up. To visualize how these continents move apart, let's have again another activity wherein your task is to arrange a series of 5 images showing the positions of the Earth's continents during different geologic time periods in the correct order onto the timeline. You have again 1 minute to complete this task. Time's up. Let's check your answers. 225 million years ago, all the land masses on the Earth is believed to be part of a supercontinent called Pangaea. 25 million years after, this supercontinent broke into two and was named Laurasia, the large northern continent, and Gondwanaland, the large southern continent. Several million years after this, these two continents further broke into 4 until it reaches the current numbers and locations of the continents. This activity showed the arrangement of continents over time. And as you may observe, Pangaea did not drift drastically. In fact, geophysicists reported that the drift rate was only 2.5 centimeters per year. This movement is very slow that not a single person on Earth can actually feel it. To gain the trust of the scientific community, Wegener collected diverse pieces of evidence to support his theory. The first piece of evidence he used was the fit of continents. According to him, coastlines of various continents match in a jigsaw fit. One good example of it is the observed similarity in outline of the coastlines of Eastern South America and West Africa. According to research, the best fit is obtained if the coastlines are matched at a depth of 1,000 meters below the current sea level. According to Wegener, any areas where there are gaps or overlaps may be explained by coastal erosion, coastal deposition, rises in sea level, and changes in land level experienced by our planet since continental separation. The second piece of evidence used by Wegener is the fossil evidence. According to him, when continents are put together, the areas where some fossil organisms were found match across the joint. One good example of this is the discovery of Mesosaurus remains, a freshwater crocodile-like reptile in South Africa and Southeast America. According to scientists, this finding suggests that South America and Africa were connected during the early Permian period, since it would have been physiologically impossible for Mesosaurus to swim between continents. Another fossil discovery which supported continental drift are the fossils of Glossopteris, a woody seed-bearing shrub or tree found in Australia, South Africa, South America, India, and Antarctica. Based on observation, when the continents of the southern hemisphere are reassembled into the single landmass of Gondwanaland, the distribution of the Glossopteris fossil form a linear and continuous patterns of distribution across continental boundaries. The third piece of evidence was the landforms and rock layers found on different continents which are oceans apart. For instance, Wegener discovered that identical rocks could be found on both sides of the Atlantic Ocean. These rocks were of the same type and age. Wegener understood that these rocks had formed side by side and only broke when the continents started to move apart. Wegener also matched up mountain ranges that had the same rock types, structures, and ages, but are now on opposite sides of the Atlantic Ocean. The Appalachian of the eastern United States and Canada, for example, are just like mountain ranges in eastern Greenland, Ireland, Great Britain, and Norway. Wegener concluded that they formed a single mountain range and was only separated as the continents drifted. The fourth piece of evidence used by Wegener is climate. He discovered that some continent carries with it the fossils and rocks that formed at its previous locations. For example, tropical plants were found in areas that are considered Arctic or frozen today. Likewise, evidence of glaciers were found in areas that have temperatures far too mild to have glaciers. This indicated that the continent must have moved. For instance, Europe might have drifted from near the equator to its present location, and Africa from the polar region going to the equatorial region. However, despite all the evidences presented by Alfred Wegener to support continental drift, this hypothesis was rejected by scientists during that time. Why? Because despite proving that the continents really drifted, he could not explain what mechanism pushes or pulls the continents apart. Wegener died at the age of 50 while on an expedition in Greenland without seeing his theory accepted. Decades later, after the death of Wegener, the idea of continental drift resurfaced. During this time, sonar technology adopted from the World War I made it possible to thoroughly study the Earth. They discovered that the Earth's crust is divided into so many pieces, contrary to what was previously believed that it is a single solid continuous land. Based on this discovery and Wegener's original idea of continental drift, J. Wilson proposed the theory of plate tectonics. According to this theory, Earth's crust is broken into roughly 20 sections called tectonic plates on which the continents ride. It also explains why Earth's continents are moving, the loophole of continental drift hypothesis. Since this theory is more complete, it has gained widespread acceptance among scientists. Advancement in technology during that time also discovered that Earth's crust is generally divided into continental crust, or the crust under which the continents are built, and oceanic crust, or the part that makes up the seafloor. In general, continental crust is composed of granitic rocks which are made up of relatively light materials such as quartz and feldspar, while oceanic crust is composed of basaltic rocks which are much denser and heavier. Plate thickness also varies greatly, ranging from less than 15 kilometers for young oceanic lithosphere to about 200 kilometers or more for ancient continental lithosphere. The variations in plate thickness are nature's way of partly compensating for the imbalance in the weight and density of the two types of crust. Another significant information discovered by the plate tectonics theory is the three main types of tectonic plate boundaries, which are convergent, divergent, and transform. Let's discuss them one by one. At convergent plate boundary, plates collide with one another. At this type of boundary, continental crust is created while oceanic crust is destroyed as it subducts, melts, and becomes magma. Examples of areas where this type of boundary can be found are the boundary between Eurasian plate and Indian plate at the Himalayas, and the boundary between Nazca plate and South American plate along the west coast of South America. The second type of plate boundary is divergent plate boundary. At this type of boundary, magma from deep in the Earth's mantle rises towards the surface and pushes apart two or more plates. Examples of areas where this type of boundary can be found are the boundary between Pacific and Antarctic plates and the boundary between African plate and Arabian plate in the Red Sea. It is even believed that if the plates found in Africa continue to diverge, millions of years from now, Eastern Africa will split from the continent to form a new landmass. The third and last type of plate boundary is transform plate boundary. It is located in areas where two plates grind past each other in opposite directions along what are called strike-slip faults. Examples of zones where this type of boundary can be found are the boundary between Pacific Plate and Australian Plate crossing New Zealand, and the boundary between Pacific Plate and North American Plate in California. Movement in each type of plate boundary generates distinct geologic processes and topographic features. For example, when one continental plate converges or collides with another continental plate, subduction will not happen since both plates are too buoyant to subduct. Since it has nowhere to go but up, this creates some of the world's largest mountain ranges. Magma cannot penetrate this thick crust, so there are no volcanoes, although the magma stays in the crust. Examples of topographic features formed because of continental to continental convergence are the Himalayan mountain range in India and the Appalachian Mountains in Canada. When oceanic crust converges with continental crust, the denser oceanic plate plunges beneath the continental plate. This process is called subduction. The subducting plate causes melting in the mantle. The magma rises and erupts, creating volcanoes. With such, subduction zones have a lot of intense earthquakes and volcanic eruptions. Examples of topographic features formed because of oceanic to continental convergence are the volcanoes in the Andes and Cascade Range found in the Pacific Northwest. When two oceanic plates converge, the older, denser plate will subduct into the mantle. Subduction of an ocean plate beneath another ocean plate results in a volcanic island arc, an ocean trench, and many earthquakes. Example of topographic features formed because of oceanic to oceanic convergence is the Marianas Trench, wherein the fast-moving Pacific plate converges against the slower-moving Philippine plate. When a divergent boundary occurs beneath two thick continental plates, the pull apart is not vigorous enough to create a clean single break through the thick plate material. Here, the thick continental plate is arced upwards from the convection current's lift, pulled thin by extensional forces, and fractured into a rip-shaped structure. As the two plates pull apart, normal faults develop on both sides of the reef, and the central blocks slide downwards. Shallow focus earthquakes occur as a result of this fracturing and movement. Early in the reef forming process, streams and rivers will flow into the sinking reef valley to form a long linear lake. As the reef grows deeper, it might drop below sea level, allowing ocean waters to flow in. This will produce a narrow, shallow sea within the reef. This reef can then grow deeper and wider. If rifting continues, a new ocean basin could be produced. Example of topographic features formed because of continental to continental divergence are the East African Rift from Jordan to Africa and the formation of Baja California. When a divergent boundary occurs beneath oceanic lithosphere, the rising convection current below lifts the lithosphere, producing a mid-ocean ridge. Extensional forces stretch the lithosphere and produce a deep fissure. When the fissure opens, pressure is reduced on the superheated mantle material below. It responds by melting, and the new magma flows into the fissure. The magma then solidifies, and the process repeats itself. Effects that are found at a divergent boundary between oceanic plates include a submarine mountain range, such as the Mid-Atlantic Ridge, volcanic activity in the form of fissure eruptions, shallow earthquake activity, creation of new seafloor, and widening of ocean basin. Example of topographic feature formed because of oceanic to oceanic divergence is the Mid-Atlantic Ridge in the Atlantic Ocean. As the plates rub against each other, like in the case of plates in transform plate boundary, huge stresses can cause portions of the rock to break, resulting in earthquakes. Places where these breaks occur are called faults. Effects that are found at a transform boundary includes a fault valley, undersea canyon, and deep focus earthquake. A well-known example of a transform plate boundary is the San Andreas Fault in California. Before we proceed with your assessment, let's have first a brief recall of what we have discussed. First, the arrangement of continents today is different from how they looked like 250 million years ago. Second, continental drift hypothesis is the hypothesis that the Earth's continents have moved over geologic time relative to each other, thus appearing to have drifted across the ocean bed. Third, the evidences Wegener used to support his claim regarding the possibility of a supercontinent or continental fit, fossil evidence, glacial evidence, and landforms and rock layers. Fourth, continental drift hypothesis was rejected by the scientific community because it failed to explain the mechanism that causes the continents to move apart. Fifth, plate tectonics theory states that all of the Earth's surface is made of tectonic plates that move, causing major geologic events along the boundaries between them. And lastly, the three types of plate boundaries are convergent, divergent, and transform plate boundary. And each plate tectonic movement creates topographic features such as mountain, volcanoes, island arc, ocean trenches, rift valleys, oceanic ridges, fault valleys, undersea canyon, and earthquakes. Let us now test your knowledge. I want you to analyze each statement as I read them, choose the letter of the correct answer, and write it on a piece of paper. You'll be given 5 seconds to answer each question. Let's begin with question number 1. The theory of continental drift states that all the continents were once part of one big landmass called Pangaea. What is the name of the scientist who came up with this theory? A. Albert Einstein. B. Alfred Wegener. C. Bill Nye. D. Harry Hess. The correct answer is letter B. Alfred Wegener is the German polar researcher, geophysicist, and meteorologist who proposed continental drift theory. Question number 2. What type of boundary exists when two plates are pulling apart? A. Convergent. B. Divergent. C. Obtrusive. D. Transform. The correct answer is letter B. Divergent plate boundary, from the word diverge, which means to move apart in different directions from a common point. Question number 3. What forms when two continental convergent plates push together? A. Earthquake. B. Island. C. Mountain. D. Volcano. The correct answer is letter C. Since converging continental plates are too buoyant to subduct, it has nowhere to go but up, which leads to the formation of mountains. Question number 4. What does the theory of continental drift states? A. Continents are stationary and do not move. B. The continents were once joined in a supercontinent and have moved over time. C. The Earth is broken into lithospheric plates that move due to convection currents. D. None of the above. The correct answer is letter B. Continental drift theory states that the continents were once joined in a supercontinent called Pangaea and have moved over time. Question number 5. Which of the following is not a divergent plate boundary? A. The East Pacific Rise. B. The Great Rift Valley of East Africa. C. The Mid-Atlantic Ridge. D. The San Andreas Fault. The correct answer is letter D, because the boundary where San Andreas Fault is located is an example of a transformed plate. Question number 6. What is the name of the Mesozoic supercontinent that consisted of all of the present continents? A. Eurasia. B. Gondwanaland. C. Laurasia. D. Pangaea. correct answer is letter D. Alfred Wegener named the supercontinent Pangaea, which means all land. Question number 7. Which of the following are not associated with convergent plate margins? A. Deep sea trenches. B. Shallow focus earthquakes. C. Island arc. D. Rift valleys. The correct answer is letter D, because Rift Valley is associated with a divergent plate margin. Question number 8. I once saw a bumper sticker that said Reunite Gondwanaland. Which of the following would not be part of this reconstruction? A. Antarctica. B. Australia. C. India south of the Himalaya. D. North America. The correct answer is letter D, because North America is part of the large northern continent called Laurasia. Kindly type in your scores in the comment box below so I can see how well you understood the topic. Very good. Most of you got a passing score. If you still have some questions or point of clarifications about our topic today, you may ask your respective subject teachers about it during your follow-up discussion tomorrow. I hope you learned a lot today. Thank you for watching and listening. See you again on our next live stream session. And together, let us continue to discover the marvels of planet Earth.